Hi, I'm Patrick Hall. I work in machine learning and data mining at SAS, and today I'm here to do the second part in the Big Data Matters webinar series. Today we're going to be talking about deep learning, which is a kind of newer area in machine learning. And first we're going to do some background in machine learning, then we're going to move into a little bit of summary of deep learning, and then we're going to focus on some SAS software that will allow you to do deep learning. Here's two definitions of machine learning. I think they're both good. But basically, machine learning is about training mathematical algorithms to recognize patterns in data, and then having those same algorithms being able to predict patterns in new data. So we usually call the data that we use to fit the model or train the model the training data. And then this new data that we try to find the same patterns in is called the score data or the test data. Machine learning is kind of a buzz term right now, and that's great. There's a lot of cool things going on in machine learning, but it's something that's been around for a long time. Some of the original algorithms in machine learning were proposed and invented in the late 1950s, early 1960s. One other thing I'd like to point out about the definitions, SAS's definition highlights automation, which I do think that's an important thing to bring up. You know, you can have this wonderful algorithm that you've spent so much time training and perfecting, but if it's not, you know, helping you make decisions in kind of an automatic way, then you're not going to get all the value out of it that you put into it. So that's an important thing about machine learning, I think, in the modern context, is you really want to be able to deploy it in a production system and get decisions from it automatically. Why would I do machine learning? Why would I use machine learning? Well, I'm going to claim that machine learning is best applied when you care more about the predictive accuracy of your model than you care about the interpretability of your model. So just think about your problem. You know, think about the problem that you're trying to solve. These machine learning techniques tend to be black box sometimes, so it's hard to understand what's going on. But they also tend to be very, very accurate. And we know that we can always fall back on a more traditional regression model if we need to use more interpretable models. So just think about your problem and think about what's important in the context of your problem. You know, where is machine learning applied? Well, machine learning is applied in a lot of different places, doing a lot of different things. Today we're going to talk mostly about pattern recognition, though. And so when I say pattern recognition, I mean things like facial detection, voice recognition, identifying handwritten text, which is something that we're going to get into later. And I think another thing that people pick up on, you know, if they're just kind of getting into machine learning or hearing about machine learning for the first time or hearing about machine learning again, you know, I think there's some confusion about, what is machine learning, what is data science, what is data mining. And if you're confused about that, then you know, we made this graphic just basically saying, yes, you know, there is a lot of overlap in these fields. And, you know, personally, I wouldn't spend too much energy trying to figure out, you know, if today I'm doing machine learning, but yesterday I was doing statistics. You know, like I said, just you want to pick the right tool for the job, and sometimes machine learning is definitely the right tool for the job. One interesting thing I think to point out about this slide is I dug this up, actually. SAS has had this since 1998, and we did add data science. We did add data science for this presentation, but you know, just kind of getting back to machine learning being something that's been around for a while and even out in commercial application for a while. So what I want to do with this slide is I want to focus on the intersection of data mining and machine learning, which is a very rich area for machine learning algorithms. Okay, we're going to zoom in, and what I'm trying to do with this slide is, you know, the gray circle represents data mining, And then the hollow blue circle represents machine learning. And so the sort of the gray part of the slide that's encircled by the blue line would be the intersection between machine learning and data mining. And there's a lot of cool algorithms in there. Okay, and we normally talk about these algorithms in 3 categories: supervised, unsupervised, and semi-supervised learning. Now, supervised learning means we have the luxury of having a target variable, or a Y variable, or a label variable. And if you've ever done regression, just a simple linear regression, then that's an example of supervised learning, be it a very kind of basic example. And within supervised learning, we usually talk about prediction and classification. So prediction means I'm trying to predict a numeric value. So, an example of a prediction question might be, how much is a customer going to spend? Classification, on the other hand, is when you have a nominal label for your target. So, an example of a classification question is, is this customer going to spend money? Yes, no. What is this customer going to spend money on? A, B, or C? Next, we talk about unsupervised learning. And unsupervised learning is when you don't have the luxury of having a target variable. So you have to learn something from the data on its own. And in unsupervised learning, we talk about clustering a lot. So if you've done k-means clustering, that's a basic example of unsupervised learning. Since you don't have a target variable, there's only so much you can do. Clustering being one of them, and then the others being what I call feature selection and feature extraction. So with feature selection, if I have my input data set with no target, I'm just trying to figure out which of those inputs I think are the best and sort of select them over others. With feature extraction, I'm trying to take the input features and combine them in some way to make new features that are somehow more representative than the variables themselves. Now, the last category that we talk about is semi-supervised learning. And in semi-supervised learning, we oftentimes have some labeled data and some unlabeled data. And we sort of assume that the labeled data is more difficult to get than the unlabeled data, and we're going to augment what we can learn with the labeled data with the unlabeled data. And that's why I have prediction and classification and clustering starred, because you usually kind of combine those 2 approaches to do that. But there are some algorithms that just get to a solution directly, and we're going to be focusing on one of those today called autoencoders, which is a type of neural network. I just put these up here very quickly. I just wanted to point out there are some things in machine learning that aren't a part of data mining. They're more abstracted from the data. Okay, so on to deep learning. What is deep learning? So basically, deep learning is just neural networks with many layers, and they have different kinds of architectures and different new optimization routines. And what ends up happening in each of these layers is that each layer becomes an optimally weighted, nonlinear combination of the inputs. And if I start from the lowest, deepest layer of a neural network with many layers and kind of work my way up, if in each layer, each subsequent higher layer is becoming a compressed higher level representation of the things below it, you can do some pretty interesting things when I start stacking those layers on top of each other, and that's what we're going to get into with our example. Okay, so what's the big deal about deep learning? Why would I use deep learning? Well, it's proven to be extremely accurate, especially in pattern recognition. And then, okay, so that's the supervised aspect of it. And then we have the unsupervised or semi-supervised aspect of it as well, where we are doing feature extraction and dimension reduction. And again, we're seeing some really kind of breakthrough results in terms of feature selection or compressing the input data. And especially a lot of this is occurring in the pattern recognition field, so with things like photographs, videos, sound, text, a lot of cool things going on with deep learning. So we're gonna do some deep learning, or we're gonna talk about doing some deep learning. All right. So how are we going to set our experiment up? Well, we need to look at our training data, which will be sort of the classic machine learning data, and that's the MNIST data, which is a database of handwritten digits, and we'll actually show you that data. Then we're going to train a denoising autoencoder network. So it's sort of a special kind of neural network, and we're going to use it to do semi-supervised learning. So we're going to use it to do feature extraction. And I personally just think there's kind of more interesting material from the semi-supervised side than from the supervised side. And you can always take what we're going to do today and take what we're going to learn today and use it to do prediction later. Then we're going to take our trained deep neural network, and we're going to use it to extract features, and that will be the plan for the experiment. Okay, so the MNIST training data, it's like the classic data that everyone kind of cuts their teeth on in machine learning. So there are 784 inputs, and they form this 28 by 28 digital grid, which represents where people have drawn little handwritten digits 0 through 9. And then the 784 inputs that represent a 28 by 28 grid are allowed to vary from 0 to 255. And that's the degree to which they're colored in. And in the form that we're using today, there's many forms of this data all over the internet. It's easy to get. We're going to use 60,000 labeled training images, and then 10,000 unlabeled test images. This is where you can get the code if you want to play along. So let's go ahead and take a look at some of the software. Okay. So here we actually see the training data. You'll notice there is a label variable, and we're not going to use that today. We're going to do this in sort of a semi-supervised way, and we're not going to use the label at all. We're going to force this deep neural network that we make to learn something about the data on its own. So if I take a closer look at the data, I'll see that it starts with pixel 0. Goes all the way over to pixel 783, which makes 784, going from 0 to 783. Oh, and if we look here, we can see where some of the pixels are colored in. And this first pixel, pixel 0, would be one corner of the data, and then the last pixel on the row would be the opposite corner. And each row is a picture. Okay, so let's get back to the slides. Here we go. So this is the neural network architecture that we're going to be focusing on, and it's a little different from maybe architectures that you have seen in the past. The biggest difference might be that we're going to use the input data as the inputs, but we're also going to use the input data as the outputs, and sort of hence the name autoencoder. You'll also notice that I've said denoising autoencoder, and that's just kind of a tweak that we do to prevent overtraining. And what that means is I've taken the input data and I've added some random pixels into it. And what that does is it keeps us, and if you look at the slide, if you look very carefully, you'll see that the numbers on the bottom are a little bit of a distorted version of the numbers on the top. So another important thing here is the hourglass shape. And what that allows us to do is go from the high dimensional, the 784 dimensional space, down to whatever dimension that is in the middle. So today we're going to do 2 dimensions just so we can plot a picture. Another thing I'll point out is these labels, H1, H2, up to H5. Those correspond to the code, and they correspond to the hidden layers as I've defined them in the code. And I've tried to make the slide fairly accurate, but I can't. I think in the code, the first hidden layer and the 5th hidden layer have 300 hidden units, and the 2nd and the 4th have 100. So I just couldn't get 300 circles on this PowerPoint slide. But with that said, let's go ahead and take a look at the code. One of the first things I'll point out is that this has been run multi-threaded. It takes too long to run today. This has been run multi-threaded, and that's always a luxury if you can do that. It dramatically cuts down on the training time. Now, the next block of code, I've defined a neural network in this hourglass shape, and it goes from 300 hidden units on the 1st and 5th hidden layers to 100 on the 2nd and 4th, all the way down to 2 in that middle layer. And like I said, what that does is it allows us to project from high dimension to low dimension, and that's going to be an important part of our experiment. Another thing I'll point out is that we are setting up the weights. We're just going to initialize them randomly. That's the next lower block of code that you might be seeing in the code. So we're gonna set up the architecture of the network the way it is on the slide, and then we're going to initialize all those weights in the hidden units to random. Okay, and we can get back to the slides. We've sort of set up this architecture. We've seen a slide of it. We've set it up in the code, and now how do we train this thing? How do we train this thing? Well, we use the inputs as the target. So basically the same data, and like I said, we added a little noise into the inputs to prevent overtraining. This is a very high capacity model that could actually learn the identity function of the training data, and that's not really what we're interested in. We would like it to be a little bit more generalizable than that. So that's, we put some noise in the input data, but generally it's the same data used as inputs and targets. We have to train it layer by layer, and that can be kind of tricky if you're not used to it, and I have a slide next that I'll try to share some details about that. What that means is each layer is trained using the inputs from coming out of the layer below it. So, and that works with the exception of the actual the first hidden layer, which its inputs are just the training data. And once we've trained every layer by layer, using the data coming in from below as the inputs, then we can stack them all together and retrain the whole network stacked together. And let's kind of talk about what I mean, training layer by layer, because I think that can be confusing. Let's try to eke some detail out of that. So since this is an autoencoder network, what's coming out of the layer below is really just going to be some numbers, and this picture is pretty accurate. So I have here a middle hidden unit with some smaller number of units, and then I have layers with 10 hidden units on either side. And so whatever's coming in to this sort of piece of the network is going to have 10 inputs. And then we're going to train those middle weights using the same data, that comes in from below. We're going to use the same data above to train the weights of that middle layer. And we're going to do this for every single layer in the autoencoder network, and then we're going to train them all. We're going to let them all kind of see each other, see where they've ended up, and re-optimize and find a new sort of optimal weighting after they've each been trained separately. Okay, so we can look at the code again, because the SAS software for this has has kind of a nice way of doing this. We built our network, we defined it, we set all the weights to random to begin with, and now we're going to start training. So, remember I said we're going to train layer by layer. How do we do that? Well, we have this nice syntax where we can freeze. We're going to freeze the top 4 hidden layers, and we're just going to train that first one. That's the first block of code. Then the next one, we're going to thaw. We're gonna thaw the next layer and freeze the one below it. So now we're training that next layer up, and that pattern continues all the way till we go through all 5 layers, and then we thaw all the layers that remain frozen, that were frozen from before, and we let them all train together. And then the last thing, I guess there's 2 interesting things here. So one, we're going to save the score code for this network, which will be important when we do our feature extraction later. And then we're also going to save the weights, which we can read back in later, which can be important for sort of subsequent steps like prediction. So let's get back to the slides. We're going to do an experiment, so we need some hypotheses, and these are going to be my hypotheses. And they're sort of centered around how can I know that I have this big crazy neural network, how can I know it's trained right? So I'm going to hypothesize that we'll know it's trained right if we can see that the hidden units are becoming filters for the images, and that's just nice. I'm not sure you could always see something like that, but we can today, because our training data is images, and we're gonna hope in our experiment that some of the hidden units become filters that we can understand, image filters. That would be one way that we knew our network had done the right thing. And then remember our hourglass shape. So, the hourglass shape allows for projection from high dimensions to low dimensions. And if the features we extract from that high dimensional space, or from the low dimensional space coming from the high dimensional space, are somehow contain a lot of information, if we can somehow compare them to a control and see that they contain more information, then that's another way that I think we'll have proven to ourselves that our neural network was trained accurately. Okay. So again, here's our picture that we've seen many times, and I just want to focus on one part of it. And this gets back into the filtering. What if we can somehow see what these hidden units were doing? Well, we're going to zoom in on this one little piece of the architecture, and we're going to try to see what's going on in there. Okay, so we've zoomed in, and we're looking at the first hidden unit and the target. So and those can say target 1, target 2, or they could say pixel 0, pixel 1, pixel 2. That's really what we're talking about. And since this neural network architecture is a fully connected graph, we know that there's a weight from that last hidden unit and the last hidden layer, H51, to every single target variable. And what that means, if you think about it, is that then we sort of know the space of those weights, and we'll be able to plot them in a way that makes sense to us. But, let's remember some things. This is, like I said, a fully connected graph. So there's a weight from every single hidden unit in that last hidden layer to every single output. Remember that. And then also, we can't remember they're also coming in from the hidden layers below. So there's a ton of connections going on, and that's what gives us all this nonlinearity. And we want to dial this back to a picture we can think about as people, and we're just going to focus on the connections from this last hidden unit or first hidden unit and the last hidden layer to the outputs. And if we remember, there's weights, and we know that there's the same number of weights as there are pixels, and we can plot them. And what happens when we plot them? Well, I think it's pretty amazing. So we see, and I'm just going to put this picture here of an 8. I'm just kind of hinting that to me, these weights look like the negative of an 8. So I would say that they have become filters. And like I said, we're just plotting the weights. This is something the neural network picked for itself. And remember, we didn't use any labels to train this data. So the network somehow uses this first hidden unit and the last hidden layer as some kind of filter of an 8, possibly. You might see something different in that picture. I'm going to claim that it is actually a filter. To me it looks like we're filtering these images, input images somehow. And then I think especially this is just kind of a random sample of the weights. And so, where each picture is all the weights from one of the hidden units. So I think if we look at all of them, it's not just this one that's a filter. They all kind of look like filters, and some of them even look like filters that I as a person can understand. Like I think the one right in the middle kind of looks like a 6, and then there's obviously some more abstract or kind of higher level filters that the network picked for itself. And what we think is going on here is that the network is able to use these filters that it's made. Each hidden unit is a filter, and it's able to combine these different filters kind of as a dictionary and combine them with the input data to make the output data. And in this case, we know that the output data are images. And so it's able to take the input images, combine them with these filters that it's made, and make the output images, which to me is just super cool, especially because the neural network had no idea that these were little 5, 6, 7s. It just sees bits, it just sees zeros and ones, and then all of a sudden we're ending up with these cool filters. So to me, this is an indication that the neural network, the denoising autoencoder network, has actually been trained correctly, and we're well on our way to extracting some features. So let's see what happens. Now we're really going to get at these features. How do we do that? Well, basically you just break the network in half to get access to those 2 hidden units. And again, I've tried to be as clear as possible, but I couldn't get I just couldn't get 300 dots on this PowerPoint slide. So what we do is we run the pixels through the first 3 layers, and we're just interested in the numbers that are coming out of these this middle hidden layer. And we're just going to get 2 columns of numbers out, and so we're going to be able to plot them X, Y, 2 dimensions. And it's going to be really interesting what we see. We're going to go and take a look at the last portion of the code. It's this block here. It's very simple, actually. It was because we were able to save the score code out. And so I'm going to take the training data, and I'm going to run it through the score code. And all I'm going to keep is I want to keep that label because I want to be able to identify groups in these extracted features, if there are any. And you can see I'm keeping the label, and then I'm just keeping H31 and H32. And that H31 and H32 means give me the first 2 and the only 2 hidden units in that 3rd layer. That runs very quickly, but all this is kind of pre-baked today. What happens when we do this? Well, to me, it's just another really cool thing. So one side of this, one of these graphs, I've just taken the whole training data, and I've used a more sort of classic dimension reduction technique, principal components analysis. It's a linear projection from a high dimensional space to a low dimensional space. And it's fairly, you know, I can see where the ones are. The ones are the red dots. They're kind of on the nose of that overlapping picture. And then on the other side, I do sort of see zeros and sixes, which are the blues. And I guess in some way that's intuitive that the ones would be as far away from the, you know, zeros and sixes, but everything in the middle of the principal components plot is just kind of a mess. You know, I can't really make anything out. But if I look at the features that were extracted with the denoising autoencoder, I see a totally different picture. I see a clustered picture. I see a picture where the groups are somewhat separated, and you know, and it's also intuitive because I'm seeing the zeros by the sixes. You know, if I think of how people draw zeros and how people draw sixes, I can see that there would be some overlap. Zeros on the totally opposite side from the ones. Ones are really close to the sevens. Sevens are close to nines. There is a little bit of overlap right in the middle, but it's much more separated than the principal components picture. As an algorithm, you know, is it going to be easier to guess in that kind of overlapping mess, or is it going to be easier to guess in the clustered features that we extracted from the autoencoder? I think the obvious answer is the features extracted from the autoencoder are going to lead to better predictions, which is typically the next step. Even though you could just use this for visualization or dimension reduction or compressing your data somehow, that's a completely valid use. But where most people would want to go from here, I think, is prediction, and that's kind of the next step. Kind of concluding our deep learning experiment, I think that we did successfully train this autoencoder to understand a high-level representation of the data. And we didn't use any labels. We just used the data itself. So the network was somehow able to learn something intrinsic about the data on its own. It turned the hidden units, especially in that last hidden layer, into filters that we were able to look at. And then the features that we extracted were clustered, and they were pretty separated, and I think that they would lead to some really accurate predictions, and I actually know they would lead to some really accurate predictions, and that's kind of the next step. You know, where do I go from here? So you should try a pattern recognition project. They're all over the internet. You know, there's data all over the internet. There's contests all over the internet, and then of course there are very practical business uses for this as well. You can, I've showed you how to extract these features, and you can take those and use those in a predictive model. You know, the most simple thing would be to take these features and just run them through a random forest, or just run them through a support vector machine or another neural network, and see what you get. Now, the sort of deep learning, something that people have been talking about in the literature, and I pointed this out in the code. I can save these weights from the trained autoencoder. I can save them out and use them again. And one thing people have been talking about is using the weights from a network that was trained in this sort of unsupervised or semi-supervised way, and using that to initialize the training of a new network that does supervised learning. So that's something else you can try. And then, of course, who just uses one model anymore? So you can ensemble these, you can use different features, you can use different models, and kind of let the models fight it out, and let the models sort it out as to how to best classify these digits. Machine learning resources. Of course, SAS has some material online about the products that we offer. Then there's a paper, support.sas.com/saspresents, that goes along with the sample code that I referenced. Hits on some of the stuff, hits on a couple other interesting things. And then, of course, there's the rest of this Big Data Matters webinar series. All right, and that's all we have today. So thanks for tuning in, and we hope that you'll tune in to more of the webinars in this series.